Hi everyone. This is a supplement to lecture 16, which is about the stress tensor and the rate of strain tensor and calculating forces in moving fluids. And today I'm going to show you an example of how to do that in simple shear flow. So hopefully by now simple shear flow is familiar to you. Let me go up here and pick this guy and make sure it works. Yeah, it does. Hopefully simple shear flow is familiar to you. So here we have two parallel plates. The top plate is moving with velocity u. The plates are separated by a gap h. And here the coordinate system I've set up is x is in this direction, y is in this direction. So y is 0 is down here, y equals 0 is up here. I'm going to call x equals 0 here, and x equals L at the end of my plate. And in simple shear flow, which I'll approximate with SSF, I have a constant pressure throughout the flow. My x component of the velocity is given by u over h times y, and my y component of the velocity is 0, so I have no y velocity. And I also, in this geometry, I'm going to give a plate an area. I'm going to make it rectangular with length L and with width W, and I'll use that so I can calculate a force at the end of the calculation. So what I'd like to do is to do a couple steps to show you how to calculate force by building up all of these different quantities. So the first thing that we're going to do here, part A, is I'm going to calculate the rate of strain tensor. So calculate the rate of strain. So in the rate of strain tensor, if you recall, is this guy gamma, which is equal to 1/2 grad V plus grad V transpose. And you can go ahead and work this all out if you want, but if you don't want to, you can use your book. And if I remember correctly, it's in chapter 6. I think it's page 139, or it's close to there. I think I was just looking this up, so I think that's why I know it's page 139. But I will just save us the trouble and write out what it is. It's dvx dx in this corner, and down in this corner I'm going to have dvy dy, and then the off diagonals I'm going to have a 1/2 dvx dy plus dvy dx. And that's going to be the same in both of those diagonals, dvy dx plus dvx dy. And notice that the order that sum happens in doesn't matter. I think in the book it's written like this or backwards of this, but either way it doesn't matter. So to calculate the rate of strain tensor, what I need to do is take derivatives of my velocity field. So I need to evaluate each of these derivatives. There's 4 of them. So I have dvx dx. So I look over here and I'm going to take the x derivative of vx, which is u over h times y. Well, this doesn't depend on x, so that's 0. Then I'm going to take dvx dy, so that's d dy of u over h times y. That will give me u over h. That's just a linear function. I take a derivative with constant times y, I get the constant out front. Now I can do the same thing for the y derivatives. I have dvy dx. If I look over here, that's the x derivative of 0. That one's pretty easy. And I'm going to get the same thing here, dvy dy. This is going to be the y derivative of 0, which is also 0. So now I take these 4 terms and I plug them back up in here. So I get gamma is equal to dvx dx, that's 0. This is 1/2 dvy dx, dvy dx is 0, plus dvx dy, that was my guy that was non-zero, that was the u over h, and I have a 1/2 there, so it's u over 2h. So let me just rewrite that, u over 2h. This one in the bottom corner is the same as the one in the top corner. That'll always be the case. This is a symmetric matrix. So it's always going to be the case. And dvy dy is right here, and that one is 0. So our first step to calculating the force is to calculate the rate of strain tensor, and we've just done it. And maybe I should back up and sort of say why we're calculating the rate of strain tensor. What I want to do at the end of the day is evaluate this expression, right? The force is NA dot sigma. So I need to find sigma. Well, sigma, which is the total stress tensor, is minus delta P plus tau, where tau is the viscous stress. And I need tau equals, or I know that tau equals 2 mu gamma, where gamma is the rate of strain tensor. So in order to calculate the force, I need to first evaluate gamma, then I can evaluate tau, then I can evaluate sigma, and then I can evaluate F. All right? So that's how I'm going to calculate the total force. So while we have gamma, I want to make a quick aside. I'm going to do this as part B. A quick aside and say, what can we do to calculate, how do we calculate the local deformation? Which I want to say is S local. Right? So this is just a little aside, but remember that to calculate the local deformation, S local, I need to evaluate this guy, P dot gamma dot P, where P is equal to some vector L divided by the norm of that vector L. So in this case, for this example, I'm just going to specify an L. I'm going to say that the L is 1 over root 2, 1 over root 2. So that's a vector with a 45-degree angle. So you can see I've drawn it up here. That's L. Okay, and I'm going to ask, what's the local deformation at that point? Now suppose I told you also that I wanted to evaluate at x equals L over 2 and y equals h over 2. Now, if this gamma depended on x and y, I would plug in L over 2 and h over 2 and evaluate gamma at that point. But it turns out that gamma is a constant over this entire region, and so it doesn't matter where I picked it. Any point that I picked it will give me this same gamma. And now that I've picked an orientation, I just need to plug this into these expressions. So the first thing I need to find is P. P is just a unit vector where I've normalized L by whatever its length is. So the first thing I need to do then is find the norm of L, or its length. Hopefully you remember the norm from your linear algebra class, but if not, it's really pretty simple. All you do is take the square of both of these components and take the square root. It's the same as the distance formula. So this is 1 over root 2 squared plus 1 over root 2 squared. And if I can finish my radical right there. So now I just need to evaluate this formula. 1 over root 2 squared is 1/2. And the other one is another 1/2. And I take the square root of that. Well, 1/2 plus 1/2 is 1. So this is just 1. So I actually picked an example already where it was normalized, but I just wanted to go through that and show you. So now I can just take P. P now is going to equal 1 over the same thing here. It's going to equal 1 over root 2, 1 over root 2. I won't bother and rewrite it. And to find S local, I just do 1 over root 2, 1 over root 2, dotted with gamma, which is 0, u over 2h, u over 2h, 0, and again dotted with p, which is 1 over root 2, 1 over root 2. So I can now evaluate this however I want, but I'm going to pick to do the left dot product first. So I do matrix multiplication. This guy times that guy, which is a 0, plus this guy times that guy, which is going to be 1 over 2 root 2 u over h. And now I'm going to evaluate the next column here, which is this one times that one, which is same thing, 1 over 2 root 2 u over h, and this one times that one, which is 0 plus 0. And now I have this left over, the other dot product on the other side to do. So I can do that. So this is 1 over 2 root 2 u over h multiplied by 1 over root 2. Well, that will give me 1 over root 2 times 1 over root 2 is 1 over 2. 1 over 2 times 1 over 2 is 1 over 4. So I have u over 4h plus, and then this is going to be the same thing, u over 4h, and that will give me u over 2h. So this tells me that the local rate of strain at that angle is u over 2h. Well, that should look familiar, and hopefully this one looks familiar to you too. Remember when we talked about simple shear flow way back near the beginning of class, we said that there was a shear stress at the wall, and the shear stress at the wall was equal to mu u over h. And so we said that was the viscosity, and that was S, the shear rate. So this u over h is coming out right there. It's modified by a prefactor because we're now doing some more exact calculations, but that works out pretty good to see that that pops out. So hopefully that makes you feel a little bit warm and fuzzy. All right, so now let's go on with our calculation that we wanted to do, and let's continue working our way to calculate the force. So we've done gamma, now let's calculate tau. So let's come over here, we can do this pretty easily. We have C, and C we want to calculate the viscous stress tensor. So to calculate the viscous stress tensor, I just have to use that formula, 2 mu gamma. So I just have to take 2 mu times gamma. Well, that is right there. So I can just pop in a 2 mu. So I have 0, 2 mu u over 2h, and then 2 mu u over 2h, and a 0 here. And look at that. My viscous stress tensor is exactly what I told you it was for the wall, which it should be 0 mu u over h, mu u over h, and 0 down here. That looks great, right? I've got that my viscous stress tensor is mu u over h, which is what we know it should be for simple shear flow. All right, we're cooking now. So let's move on and do the calculation in D here of the total stress tensor. So I'm going to come up here, do part D. Let's do the total stress tensor, which is sigma. So I said sigma is equal to minus P delta plus tau. Well, I just wrote down what tau was. What is this minus P delta stuff? So I said that for simple shear flow, P was equal to just some constant pressure, which I'm calling P naught. Maybe that's the atmospheric pressure. And delta is the identity matrix. So it's 1, 0, 0, 1. So let's just plug all that in and do the matrix math. So I have minus P0, 0, 0, P0. That's P0 multiplied by the identity matrix, plus I had my guy from before, which I remember what it is because we've done it so much, mu u over h on the off diagonals. So now I simply have to sum those two matrices. Well, that's pretty nice. I get a minus P naught in that spot, and I get a mu u over h in that spot. I get mu u over h in the bottom, and a minus P naught here. So what's going on? My total stress tensor, I have in the normal stresses, I have pressures, and in the shear stresses, I have the viscous stresses. Awesome. Okay, so now we're ready for the last part, which is let's calculate the force. And let's do it on the bottom plate. So on the bottom plate from simple shear flow. Okay, so I have to think about what's going on here at the bottom of the plate. So I have the bottom plate, and I have my equation. F is, let's see, NA dot sigma. So the area, I know the area of the bottom plate, that was LW. And I need the normal vector, the unit normal. So the outward normal is going to be what? I said this is going to be positive EY. So that's going to, I'm looking up there, that's my EY. So I simply just plug them in. Say the force is EY times LW dotted with sigma. All right, so EY, I said that, we remember what EY is. EY is just 0, 1. Or I don't even need the transpose here, just 0, 1. So I'm going to put in 0 LW, and I'm going to dot that with my total stress tensor. So minus P0 mu U over H, mu U over H, and minus P0. So now to find my force, I just have to do some more matrix math. So I do 0 times minus P0. That gives me a 0. And I do LW times mu U over H. So that's mu U, it's kind of hard to see the difference between these, over H times LW. That's my first component. My second component now is 0 times mu U over H, which is 0, plus LW times minus P naught. So minus P naught LW. So to rewrite this, my force is equal to mu U divided by H LW and minus P naught LW. So what is that saying? So this is my X component of the force, and this is my Y component of the force. The X component of the force on the Y surface is the shearing force, right? That's the force going in that direction. And that's equal to mu U over H LW. That came from my shear stress. That makes a lot of sense. That looks great, right? This is the force that's caused by those two plates, by the top one shearing the bottom one. It's giving it a positive force in the positive direction. The Y component of the force is coming from the pressure, and that's in the negative EY direction, and that equals the pressure of the fluid times the area of the plate. Perfect. So this makes sense, at least to me. Hopefully it makes sense to you. I hope I made it clear enough. So my total force is given by the X component from the shearing forces and the Y component from the pressure forces. All right. And that, again, the Y component, that's the, I just had in my notes, I wanted to say that's the normal stress, or the normal force. Okay, I think that's all I have for you.